Yeah, okay.
Okay, so good morning to everyone. So today we have Jinzhao Wang, and he's gonna tell us about beyond islands and a free probabilistic approach.
Okay, I want to thank the organizers for giving me this opportunity to talk here. I'm excited to tell you some work based on partly on my dissertation and also extension of it, and also many discussions with my advisor, Renato Renner, who's not here but will be here next week. All right, so this is the outline. So basically the topic I'm going to talk about is sort of a good continuation of what Vijay talked about yesterday, because he was alluding to something about summing over all saddles. And this is exactly what I'm going to do with the help of the free probabilistic toolkit. The problem I'm going to study is the good old entropy of the Hawking radiation. So no fancy stuff as Vijay talked about yesterday, but we're going to see there's a lot of interesting mathematics contained in this problem alone. I'm going to do this entirely in the West Coast model, namely the Pennington-Shanker-Stanford-Young model, a PSSY model. And the only thing I'm going to do that is different from what they did is that I'm going to consider an arbitrary non-flat bulk entanglement spectrum. And the problem is to compute, in that case, the entropy of Hawking radiation. And it is a question whether the island formula is still good or not. And if not, what's a better version of it? So to tackle this problem, I'm going to tell you some basics about free probability. I'm going to basically draw what I need from that vast literature for this problem only. And then I will present you the result, how exactly this entropy can be computed given any arbitrary bulk entanglement spectrum. Okay. So thanks to Vijay again, he already introduced the PSSY model, or even not. I believe everybody here knows more or less what's the model. So it's a model in 2D gravity, in particular JT gravity, where you put in some end-of-war brane to mimic the interior of the black hole, and you sort of putting by hand some entanglement with a radiation reservoir that mimics the result that Hawking find, namely you have a lot of thermal modes produced by the Hawking radiation. And so in the original model, it's important to point out that this entanglement is maximal in the original study. So yeah, like I said, we're going to consider the replicatory calculation of the radiation entropy using the replica trick. And so this is the sort of boundary conditions you set up. It has the condition about the asymptotic boundary, which has a thermal length beta, and it also has attached the end-of-war brane indices, and you're just going to contract them cyclically and try to fill in the bulk with all sorts of topologies. And the usual assumption, as in Lukowitz Maldacena, is that the dominant ones is going to be the replica symmetric ones, namely, in this case, a fully disconnected or a fully connected wormhole saddle. And these saddles will give you basically this formula. In this model is very simple. It just says you pick the smaller of the two, where k measures, log k measures the number of qubits in the radiation. And SPH the begins the Hawking entropy, and this S of R is the fine-grained entropy that you want to calculate. So this formula is actually very accurate in the microcanonical ensemble, but in the canonical ensemble where you have a finite temperature, it is subject to a correction near the transition when this two quantities are comparable. And this correction is found by summing over all saddles in the original PSSY paper. And in some sense, what I'm going to do is just a sort of a more upgraded version of what they did for a slightly more general problem. Namely, I'm going to consider arbitrary entanglement spectrum. Okay, so so why we want to consider the corrections due to near the transition? So more generally, the problem is studied in the so-called QES prescription or QES formula in ADS-CFT. Again, the derivation, the standard derivation to argue for the validity of the formula is sort of a Lucas Martesina type argument where it assumes the dominance of replica symmetry saddles. And we ask, what if there's effects of replica symmetry breaking? Would that change the story? So it is understood that, sorry, I should say that I didn't have time to put in all the relevant references. So I'm sorry for anybody's work which is not mentioned here explicitly, but yeah, I should put in future versions of this kind of talk. Okay, so it's understood that there's a corrections near the transitions of this order, and this is fully analogous to the correction to the island formula in the PSSY model we just saw. But this correction, if you can think of it as sort of a subleading correction, because the leading order is 1 over G. However, so it was pointed out by Chris and Jeff that if you have a bulk state that has a very non-trivial entanglement, or even just non-trivial correlation between the regimes you are interested, there can be large corrections to the formula, to the QES prescription. And by large, I mean, so what do I mean by non-trivial entanglement spectrum? Mathematically, it means if we look at the so-called mean entropy and max entropy and volume entropy of the bulk state, if there's a large separation between these quantities, then we expect the formula, the usual prescription would not work in a sort of large window near the transition. So because the window is large, it's no longer, let's say, near the transition. It's actually quite a significant change. I will give you an example later. Essentially, this is because the correlations in the matter sector in this state sort of enhances the effect of the other non-replica symmetric saddles. So it says you can't ignore those if you want to compute the volume entropy accurately. So this was studied in the context of ADS-CFT using some random tensor network techniques by Akers and Pennington. So we expect the same large correction to the island formula, because essentially it's sort of one can think of the island formula as a particular application of the QES prescription. And we expect this to happen when we have a non-flat entanglement spectrum in the PSSY model. So generally, you can think of this just as a more general setup one can consider. And this is actually relevant when we, if we consider applying quantum information processing to the radiation, which might change the spectrum. Or if we consider to put some interesting Hamiltonian to the reservoir, let's say the Hamiltonian has a huge gap, and if the temperature is low enough, maybe the spectrum is also not flat. Okay, so it's just a more general setting we can study the problem. So let me give you a quick example, sort of a very artificial one. If you consider a black hole in superposition in the PSSY model, namely you put two black holes with a different stage of its radiation, and the spectrum is sort of L-shaped, right? So in one branch you have a lot of entanglement, in the other branch you have a tiny bit of entanglement, and if you do the calculations that I will show you how later, you will find that the exact summing of all saddle answer give you a sort of page curve like looking like this, whereas the island formula predicts something like this. So so this agrees precisely with what Chris and Jeff found, namely the island formula is only valid in a regime guarded by these so-called one-shot entropies. These are the two extreme points of the ring entropies. So the transition no longer happens at the sort of the page time, which is usually when the log K is comparable to the bulk volume entropy. So this is, again, just a motivation why we are interested in the problem. So we're going to see how exactly one can compute the exact curve. Okay. So again, now the problem setup is just I put some arbitrary Schmidt coefficient in the PSSY model. These are no longer maximally mixed state between the brain and the radiation. And we like to sum over all saddles. So previously I just show you, sorry, this should be a replica wormhole. Okay. So previously I just showed 2 saddles. Now I'm saying we should also include this 3, for example, in the case of 3 replicas. So the rule is for each saddle, you add up all the contributions, and there are contributions from the gravitational sector when you sort of compute the partition function for these disks. So which I denote as this Zn for a n-connected disk or wormhole. And also you have a contribution from the matter sector that is due to the contraction of the index loops. Okay, so the only difference on a technical level from the PSSY work is that these index loops are now weighted by these coefficients, right? So if you do the math, they actually compute to something like this. And if you consider, say, a maximally mixed state, they just give K. So this agrees with what they had, but just more general. Okay, so this is the formula. Okay, so now let's look at what is this gravitational path integral calculation. What is given out explicitly in the original PSSY work. I'm just citing here. So this partition function is sort of just a integral over the density of states, rho e here, which is a sort of a Sinch function. And this is sort of the canonical one of JT gravity in the double scaling limit. And this integrand here, ye, is sort of a Boltzmann factor that is corrected by the tension of the brain. So remember the picture before, you have a thermal circle, but it's disrupted by the brain. So this is the disruption due to the brain, right? So you just have otherwise you just have a Gibbs distribution, but now it's disrupted by brain. So I'm a quantum information guy, so I use 2, sorry. Okay, so now we can rewrite this, right? We can rewrite this properly as at the moment of the thermal state, right? So this is just I normalize this by its trace, and we can just change our variables. We can define some distribution that is in fact bounded between 0 has a bounded support between 0 and x0, x0. X0 is basically the value of y0 divided by z1. Okay, so y is here. Okay, so this is just a rewriting of this formula. To make it manifest, it is a moment of the sum distribution. Okay, and the Bekenstein-Hawking formula is just given by, because you have this distribution, you can compute any spectral functions. Namely, you can compute, for example, the von Neumann entropy using this formula, and this is just in the limit of large tension. Yeah, this is just a formula. Yeah, but we don't need these details. Okay. All right. So so now, of course, the task is to sum over all saddles. The first thing we need to do is to try to write down a formula for the sum, right? And the saddles are organized by the so-called planar diagrams, because we're looking at a regime where K is very large and the entropy, the topological entropy in the JT gravity is also very large. So this suppresses crossings and higher genus. So for each M boundary disk, I just have a disk. I don't have handles, and I don't have crossings between bridges between these wormholes or these disks. So this is the planar limit. Again, is what the PSSY guys did to simplify the calculation in some sense. And it turns out there's some nice combinatorics in this limit. So basically the saddles are organized by the so-called non-crossing permutations, right? So here I just draw the particular saddle with maybe 13 replicas, and I consider maybe an abstraction of this diagram in terms of this kind of sort of a partition diagram. It's a partition of the set. It's a partition of a set, which I denoted as square bracket n. So this just means a set of n elements. And I put them in a circle and I partition them. And there's a one-to-one match between a so-called non-crossing partition and a non-crossing permutation, right? So first of all, non-crossing just means when I draw this diagram, there shouldn't be any crossing. And this defines me a partition of the set. And then to get a permutation, you put these blocks into a cycle notation, and where you put the smallest one in the first slot. So this defines you a particular permutation according to this cycle diagram, cycle notation. Okay. So we have essentially this bow-phase partition function, which is the overall partition function for the replica trick. It's just a sum over all non-crossing permutations, and you have in each permutation you look at how many cycles or blocks they have, and then you evaluate this gravitational partition function. And now the task is to figure out the meta sector. Yes.
Yeah. Sorry. So the non-crossing permutations form a subgroup of the symmetric group. I mean, when you multiply two of them, it's non-crossing. Is that a fact? Is NC13 a group or just a subset of the group?
I'm not sure it's a group. Yeah, but I need to look this up. But yeah, okay, yeah, I should know this. But yeah, for us it's not relevant. But it should be in Wikipedia page somewhere. Okay, so we just know that the formula looks something like this. We still need to figure out what's to put here from the meta loops. All right. So the key observation that basically motivates this work is that we realize this end of the word brain index loops define another set of cycles or partitions corresponding to a unique non-crossing permutation dual to the one that is defined, that is given by that defines the saddle. Okay, so this is called the so-called the Fourier complement of pi. Okay, and essentially the definition is just this diagram. Okay, so let's say we have this index loops, so we just put some extra red dots to represent an abstraction of these index loops, so we can translate this diagram to the diagram on the right. And the rule of the game is that, so how do you define this Fourier complement? This is exactly the same. Basically, you replicate another set, which is black originally, now in red, and interlace them. And now the black one is given. So for the red one, you try to connect as many as possible without crossing the black ones. Okay. So from the diagram, it's evident that this defines a unique complement to the original pi. Okay. And in this example, this complement is given by this cycle notation. And clearly, again, from this diagram, it's another non-crossing permutation. Okay, so with this observation, we can just organize this formula in this way. Okay, so now finally we can write down a sort of precise formula for the path integral, and it just says you sum of all non-cross permutations, and you look at the blocks in the permutation and its complement, and you somehow take the product of all this data that is given to you. Okay. And of course, the main hypothesis of the replica trick is that this Zn with appropriate normalization gives the moments with respect to some appropriate trace of a perhaps random density operator. Okay. So, so you can think of this, just define you a bunch of moments. And the point is, in what sense can we think of it as a density operator that describes the radiation? And you can sort of think of this as a machine where you're inputting some data about distribution. Here, this is the sort of the Beer radiation describing the bulk spectrum, and this is the gravitational part describe the black hole, and they are given as these moments. Okay, so your input data is the moments from which you can reconstruct some distributions. And this is the magical machine of the gravitational path integral. And this machine just sort of scrambled everything up in this complicated way and output some moments again. And the task is, of course, to figure out in what sense this is really a spectrum distribution of a density operator. Okay, yes. So, okay, yeah, sorry. Yeah. Okay. So I think I just okay. So this B is I'm going to define this in the coming slide, but this B is just actually I think I had it here. So this is this one under product.
A notation product over V belonging in pi. So pi is a non-crossing permutation.
Yeah, okay.
It's an element of a permutation.
Yeah, it's a cycle in the permutation. Here is a block, right? And here this notation means you look at the cardinality of the block, and you take the let's say the cardinality is 5. You take the fifth moment of this distribution. Okay. So this formula is just a rewriting of this formula with a bunch of definitions to make it apparently that it's about two inputting distributions and plug into this machine and outputting some data. Okay.
Thanks.
Okay. Okay. So yeah. So we will see this formula later. But now the bottom line is we want to understand this formula. We want to understand how to extract this distribution analytically. And this is basically a mathematical problem. So it turns out the relevant tool is, or the language to understand this kind of combinatorics is free probability. Okay, so some abstract nonsense, which is not so relevant, but since I'm talking about free probability, this is sort of inevitable. So a non-commutative probability space is just sort of a generalization of the usual probability space, where it's defined on a so-called star algebra, where every element has a trace. Okay, so the trace, you should think of the trace as the expectation value of the random variable, whereas all the elements in the algebra is a random variable. And more concretely, we can consider so-called finite von Neumann algebra, which is a particular type of star algebra with more structure. And tau is just a so-called tracial state. Okay, so tau is a trace in the sense that if you're putting AB here, it sort of is equal to tau of BA. Okay. So for instances, if W happens to be a factor, it's either type 1n, which is like matrices, or type 2-1. Okay, so this thing is sort of infinite dimensional matrices with normalized trace, for which you can still make sense of their traces in the asymptotic limits. In some sense, we are talking about large random matrices. So this is sort of the underlying theme of this calculation, and also it's intimately connected to free probability. So you should bear in mind that what we are talking about, maybe it's useful to think of this probability space is some infinite dimensional limiting large matrices and they form a type 2-1 algebra. Okay, but if you don't know about this, it's not so relevant. Let's see some examples of this sort of abstract definition. We can consider the classical probability space, which is just random variables which are described by the bounded functions on some homomorphic triple equipped with the usual expectation, which is sort of induced by this probability measure. And we can consider matrix algebra, where I think here is a typo. I'm missing an equality here. So basically, you consider algebra of L times L matrix with complex entries, and the expectation is the normalized trace. Okay, and you can somehow adjoin this two to define the probability space for random matrices, namely each entry is random, right? So you sort of tensor product of these two algebra, and your trace is basically you take the trace and take its expectation value. Okay, so this is just sort of saying this definition is very general, it's flexible, it is able to accommodate different sorts of notions of probability under one footing. Okay. Okay, so we're going to consider, of course, density operators. These are particular self-adjoint operators. So if we have the condition that their moments are bounded, okay, so-called exponentially bounded, so their moments does not grow too crazy, there exists some independent constant which bounds all these moments, then it's a theorem that we can always find a measure for A that matches with these moments. Okay, so these moments are just defined by the trace of these polynomials, and the theorem says you can think of this mu A as a spectral measure of A. Okay, so remember A is sort of some infinite dimensional matrices. So it sort of has for a finite dimensional matrix, we can make sense of the spectrum distribution as a sum over some delta functions, right? And in the limit of the matrix goes to very large with respect to this trace, they become some sort of continuous distribution. If let's say this is random matrices, and then basically this mu A is that. Okay, but this is sort of the other way around. It just says if you happen to have some abstractly defined notion of trace and from which you get moments, then you can always make sense of this distribution as the spectral measure of A. Okay. And of course, this is supported on the real line. In particular, it's bounded, so it's supported on a compact interval. And in fact, the converse statement also holds. If I give you a compact distribution over the real line, you can make sense of you can construct a sort of abstract probability space with a random variable that satisfies this. Okay, but this is just yeah. So the converse also holds. Okay, so so how do we make sense of entropies? Well, they're just given by the usual formulas, but there's some things, some subtleties we need to mention. If we have a self-adjoint element, and in addition, if it's positive and normalized, basically that's what you want for a density operator. And then this A you can use A to define a state, right? Basically, I mean, a state in Evolutionary algebra is just a function of acting on the algebra and map you to a complex number, and this function just defines you using a state. Okay, so in this sense, it represents a density operator. And then you just define these entropies as usual, and you can use this sort of spectrum formulas to compute this quantity. This is just equivalent, right? Because of this fact I told you. Okay. All right. So but how do we sort of draw a link between the usual density matrix that we are all familiar with? So let's consider, let's say this A is the element of the matrix algebra with respect to the normalized trace. And then the volume entropy so defined differs from the density matrix A, capital A, normalized with respect to the usual trace by a shift of log n. Oh, sorry, here's a typo. Right. So the point is here I use the normalized trace, whereas usually you take the trace without divide by n. So if you do the calculation, it would differ by a factor of log k. Okay. So so this quantity so defined can sometimes be negative. It's just a feature of sort of continuous entropy. But we just follow the definitions and they are whatever. If they take negative values, don't be surprised. Okay, because you can always add back log n in finite dimensions and get back. Yes.
Just a quick question of clarification. Does that mean S of little a is negative? Because log k would be the maximum that you could have. Presumably not log n or log k.
Yeah. So this A here is okay. The capital A is the usual density matrix. This A here is n times A because you normalize it with respect to the normalized trace. Yeah. So that's why the log is positive. So minus log is negative. Okay. Okay, so freeness. Yeah, so let's say, how about we ignore this definition? And I tell you what roughly freeness is. It's observed by Voculescu that if you have two independent sequences of random matrices, okay, so independent means their matrix, the joint distribution of the matrix elements are independent, okay? But within each matrix, the joint distribution may not factorize between each element, right? So you can have correlations within each matrix, but among these two sequences, the joint distribution is factorized, okay? So that's independence. And if you also have that they both have a convergent spectrum distribution, namely you take the sum of the deltas, right? In a finite size, your spectrum distribution is just a sum of delta functions. And if this random matrices have a convergent spectrum distribution for both of them, and furthermore, if one of them is, so the ensemble is unitarily invariant, namely, if you conjugate this each element in the ensemble by a unitary, the ensemble stays the same, then you have something magical happen, namely, they become asymptotically free, okay? So the limiting object satisfies this weird relation, okay? And I'm gonna tell you roughly what this complicated relation is. So freeness, sure, yeah.
So one of those, I've got this about the relation between A and B. So those are independent from each other, but then you only demand that one ensemble is invariant.
Yeah.
Yeah. How do those guys play with each other? Or
well,
your point is that the A and B.
Yeah, if you have one of them happens to be an ensemble that is unitarily invariant, then they will be free to each other. Yeah.
Okay, we're talking about probabilities for like products of A and B.
Yeah, so I'm gonna tell you what free means, and it sort of tells you that if you evaluate the traces of the products of them, sort of any sort of polynomials, you can compute this complicated trace in terms of the moments of individual elements. Okay, so that's something you wouldn't expect to happen in any finite dimensions. That's why you sort of need infinite dimensions, and you need these weird conditions such that in the limit somehow the trace simplifies. Okay, so the freeness using this formula I didn't explain, but let me just give you two examples of what this formula says. You can think of the freeness as a rule to compute the traces of polynomials in terms of traces of individual components, right? That you otherwise cannot compute without freeness. So let's say here it just says, I think I have an extra factor here. Here it just says tau AB is equal to the product of tau A and tau B. So this shouldn't be here. And furthermore, say tau AB is given by this completed expression. So if you think of this as finite dimensional matrices, this can never happen. Okay, but if they happen to be the limiting large matrices that are satisfy the previous conditions, then Vokulescu told you that you can actually compute the trace of any polynomial in terms of traces of individual things. Okay, so but what are the so here I didn't tell you the exact rules. So to give you the exact rule, I need to tell you another object which is called the free cumulants. So it's just like in classical probability theory, when you have a bunch of moments, you can define the corresponding cumulants, right? So I think in quantum field theory, maybe cumulants are like connected correlation functions, okay? So, but here the only thing that is different from the classical cumulants is that you don't sum over all permutations, you sum over just non-crossing permutations. So here's the mathematical definition. The cumulants is just a multi-linear map from sort of n copies of your original probability space to complex number. And this is defined by this sort of recursive relations of, so on the left-hand side, you have some moments, and you demand that the moments can be written in the form as a sum over non-crossing permutations, and where each summand is a product of cumulants. Okay, so here example where we have sort of have this, and this you can use that to define for you the second cumulant, and then you go to a higher order, you can invert this to define the third cumulant. Okay, so if you have a bunch of these equations for all the moments, you can invert them to define the cumulants. Okay, so you can already see this sort of combination, this sort of the rule here matches very well with what we saw in the gravitational path integral. So yeah, some interesting things are unfolding. Okay, so these are cumulants. Okay, so basically there's a set of cumulants defines the distribution equally well as a set of moments. Okay, they're just, you can always translate between moments and cumulants using this sort of rule. Okay. All right, so so now comes to a pragmatic definition of freeness. It turns out freeness boils down to a very simple criterion when you talk in the language of cumulants. Namely, freeness means vanishing mixed cumulants. So what did I mean? Remember, the cumulants are multilinear functions. You sort of maps several random variables to some complex number. And if you demand, if your input has different random variables that are free, then the cumulants always vanish. Okay, so this is a very simple criterion to say when they are free. You can simply check if these mixed cumulants vanish, then you know these are free to each other. Okay, so let's draw some familiar diagrams. Let's say the polynomial we consider is Galileo Galilei for GALIEO being free to each other. Okay, And then the trace of this polynomial, or this monomial actually, can be expanded in terms of the cumulants written in this way, okay? Notice you don't have cumulants where you put in different species here because freeness demand they vanish, okay? And of course, you know each cumulant from this equation, okay? So basically you can then write each cumulant in terms of moment again. You arrive at the fact that you can write the trace or the trace of or the moments of this sort of complicated monomial into individual moments of L, A, I, J, G, E. Oh, okay. And the rule is so how do I see this expansion? I simply again try to connect. I try to connect the same letters because of freeness. I'm not allowed to connect letters that are different. Okay, and I also do not allow crossings in this diagram. So if you sum over all these kind of diagrams, this gives you the expansion of Galileo Galilei, the trace of it in terms of cumulants. Okay.
Why did it take 3 of tapestry of L?
Sorry?
Why the tapestry of L?
Tapestry of L, yes. Sorry, here's L, I think. So it's yeah, tapestry of L is just a notation of tapestry of L. Okay. Yeah, okay. Yeah, so I think yeah, so no, it's just a possible saddle. So you can also have 4 L's connected. That's another. Yeah, okay, I messed up this example. So don't worry, but the idea is that basically you look at this word and you connect the same letters without crossing the other ones. In the sense, when you draw this diagram, you don't cross the other ones, and you write all possible ways of doing that. And this gives you the expansion of this moment in terms of cumulants, and that's the rule. Okay. Okay, so with this, we can finally talk about something interesting, namely, if we care about the moment of a product of 2 free random variables, A and B. I note here I put in a sort of self-adjoint positive form, namely square root of A, B square root of A, which has the same distribution as all these things. And the moment just read, you have n pairs of AB all sort of stacking up. So you can imagine a picture. How you compute this is just A, B, A, B, A, B, A, B, A, B. Okay, so maybe this is sort of reminds you of the gravitational Poisson integral picture I had before. So precisely, you can show using what I told you that these moments are precisely given by this formula. Okay, so we finally arrive at what we the problem of gravity gives us, which is to make sense of this kind of formula. But now free probability says, oh, we know this formula. This formula just says when you have 2 free random variables, it's the moments of the product of them. Okay. All right. So this operation, you can now think of this machine. It was GPI here, but now really just this notation, which is called free multiplicative convolution. This is just a machine that you feed in the data about 2 distributions. And if they are the spectrum distributions of 2 free random variables, then the moments defined by this thing would define another distribution, which is denoted as the box product. Yes.
Sorry, you must have said this and I just missed it. Why did we suddenly put square roots? Why didn't we just write A, B, or BA since?
Yeah. So I want to make a positive self-adjoint matrix.
Oh, I see.
Yeah. But you see, they all have the same spectrum.
Yeah.
Yeah.
So could you have done like 1/2 AB plus BA or something like that, or?
No. It's just okay. So the
It has to be a monomial?
yeah, it's just a monomial, and I consider nth moment of it. So I raise this whole thing to power n, and no
Oh.
matter what of these 4 options you put in, the traces always look like this.
Oh, I see. So if you did 1/2 AB plus BA, that would just have a different distribution.
Yeah,
I
it's
guess.
a different. I don't want to consider that. I just want to consider A times B.
And why does it matter that it's self-adjoint for you?
Oh, it's just because I want this distribution to be, yeah, it doesn't matter, but at the level of the distribution, it's all the same, right? Because
Yeah.
the moments are the same.
Yeah.
For me, it's just later when we talk about the states of the Hawking radiation, as suggested by this formula, we want to think of them as density operators. So we always want to, it's just nicer to have a positive operator here, right? You see what I mean? So I guess you will see why this is relevant later.
Okay.
But for this formula, yeah, you can equally well put here A times B, okay, without any troubles. Okay, so so now basically the point is we want to match the formula from free probability to the formula we had from for the partition function. Okay, but one problem is just that this mu b, remember this mu b is sort of defined from this the density of states in the double scaling limit, which is not normalizable. Okay, so meaning the integral of mu b, or the zeros moment of mu b, is infinite. So mu b is not a probability distribution. So the technical thing that I want to do is to basically undo the double scaling limit to go to finite n and work with these kind of regulated distributions, which can be made into probability distributions. And why this is important, because otherwise this formula wouldn't recognize, if you're putting here something not a probability distribution, but just some measure, positive measure over some compact support, you can't apply this formula. So there's just a technical caveat. You need to undo the double scaling limit and later take the larger limit back again. Okay, so let me just show you what's the result. The result is you just rewrite the formula we had for Zn, normalized it appropriately, and you define this. You have this thermal spectrum distributions, but now you sort of go to finite n, and this is the input data due to the non-flat bulk spectrum, and the output of the machine can be written in this form. Okay, so here basically you have some distribution which I haven't defined for you that depends on the thermal spectrum, and the matter sector. Here's just a rescaling. So this is not important. The point is, it is as if the matter sector and the gravitational sector behave free to each other in this formula, and the gravitational passing integral try to convolve them, to try to convolute them together. Okay, so this is the bottom line. Yeah, so this distribution, which I haven't defined for you, is basically something that is called the free Poisson law, which is again just a name. So what you can think of it is just that. So remember, in this formula we have cumulants instead of moments, whereas in our gravitational problem we just have moments, right? So it sort of means that we should think of one set of the moments as cumulants. Okay, so it's a bit of mind twisting, but the point is, if you claim this data, which is the moments of some distribution, to be the cumulants of something else, then this is the something else that has this cumulant. Okay, so maybe you heard of this so-called Marchenko-Pastor distribution, And this is just another name for the Poisson law. Okay. And this is sort of necessary because, as I said, this thing is really not a probability distribution. Even though you sort of regularize it, it does not blow up. But the integral of the distribution is not one. Okay, so you can't think of them as the moments of any distribution. But the point here is that you can think of them as cumulants of some distribution. And this is the way you get around this problem. So in particular, this distribution here is well defined, and also the larger limit of this distribution is well defined because the cumulants converge. Okay, so again, I have to restoring the larger limit and go back to this. So this is the final result in terms of this fancy box notations. Of course, you might just say I have told you nothing because what I did so far is just a change of notations. Okay, so what I actually want to show you in the last bit is maybe I skip this is how to actually making use of the fact that the box notations is sort of equipped with a powerful chip of free harmonic analysis. Basically, just like how Fourier transform help you to turn a convolution into a product, and then you can solve the convolution. Here, the sort of fancy free convolution comes with its own tools. There are some. It goes under the name of free harmonic analysis, and then you can use those tools to evaluate this cross product. Okay. So this is the solution presented as an algorithm. So the red part are the input to a problem, right? So mu B is the thermal spectrum, and mu R is the radiation spectrum of the bulk, which you put in, arbitrary spectrum you like. And so the first step is to solve this fixed point equation. Okay, so this is some complicated double integrals, but then for Mathematica, it's not so complicated because a fixed point equation, right? So, like a normal fixed point algorithm, you just make a guess of YZ and it's a wrong guess, and then use the output as another guess, and very quickly this will converge. So once you figure out YZ, you plug into this formula, so-called Cauchy transform, or otherwise known as the resolvent. Again, the formula just need this input of mu R. Okay, so the red are the input, the Y's are the intermediate things, and in the end, you do the so-called inverse Cauchy transform, you extract the spectrum. Okay, so I think this is the best you can get as far as evaluating the free multiplic convolution is concerned. All right, so I think I have a choice of whether to tell you about. Yeah, okay. So another question is, now we just want to do some sanity check. I present to you a sort of fancy formula, but is it consistent with the island formula, right? So we still recall the result of Chris and Jeff. They say, in regimes governed by the mean and max entropies, the island formula should still be a good approximation of whatever your complicated convolution formula is given, right? So let's consider this problem, how to do the reduction to the island formula. So let's consider, let's say, the microcanonical ensemble, where the expression of the convolution simplifies, essentially because your mu B is just a delta function, right? Because it's microcanonical, it's all flat. Okay, so this is your expression, and the corresponding spectral distribution, you can write it down. The point is that now you want to show somehow when this happens, namely the entropy of the microcanonical ensemble is below the mean entropy, which is basically the log of the largest eigenvalue of the bulk state, or when the entropy of the microcanonical ensemble is larger than the log of the rank of the bulk state, then two particular saddles dominate. So you can ignore all the other saddles. Okay, so this is sort of a consistency check to check that you actually this formula is consistent with island formula in this sort of regimes. Okay. And the way you do it is to sort of translate to the operator version, because you know implicitly the convolution formula is computing a product of a bunch of sort of free random variables, and you write this down and you translate to large random matrices, which then you can invoke something like a decoupling theorems, sort of doing some random projections. You can use some quantum information ideas to argue. Basically, the key word is one-shot decoupling, to argue that when S is very small, the island formula is correct. Okay, and also you can do the other way around in this regime by noticing that this distribution is very close to a so-called free projection, and the entropy of the output of the convolution is basically the same as the input. Okay, so this is just some consistency checks. Yeah, so I think it's sort of some technical work, but I think the outcome is sort of interesting because it sort of tells you that we should think of, the usual philosophy is we put gravitational degrees of freedom and matter degrees of freedom. When we talk about them being independent, we use a tensor product. But Freeness says Freeness is a notion of independence defined using so-called free product. Okay, so it's a different notion of independence. This calculation of the spectrum suggests that maybe, at least in this setting, we should think of them as being free. Okay, so there's a more precise version, which I didn't have time to tell you. That is, for example, in some scenarios, when you look at the page curve, it's actually generated by a semigroup of spectrum distributions described by a sort of free Poissonian process. So, usually we say the Hawking radiation is like independent modes being emitted, and this independence is captured by a tensor product. Whereas here, we say the independence is captured by freeness. Then you get page curve instead of blowing up curve. Okay. And another thing you can do is you can turn the formula, which I've tried to tell you, this convolution formula, back into a generalized entropy using some relative entropy with an properly chosen reference state. So this is something you can do. Maybe it has some deeper meanings, I don't know. Basically, the point is that so far I use this von Neumann algebra as a help to build our free probability toolkit to solve the problem in gravity. But maybe these von Neumann algebras themselves are in fact just the von Neumann algebra describing the algebra of observables. So if one can make a link there, maybe there's a better way of saying to understanding this formula. Another fun fact about this calculation is that for a very old black hole, you actually describe a random quantum channel that showcases something a quantum information theorist would care about, maybe Patrick Hayden would care about, so-called the superadditivity of classical capacity. So this is sort of some famous conjecture that is proven to be false by Hastings based on work of Patrick and Andreas. So they construct some random channel example that the only purpose of that channel is to prove this conjecture wrong. Okay, but now we see for a very old black hole, it contains a description of this channel that Hastings constructed, and this is a very interesting regime because usually if you just consider entropies in this regime, all the non-replica symmetric saddles are very subleading, and for any purposes you can think about, say computing entropies, you can neglect all these saddles, but to see the violation here, you actually need all these saddles, even for a very old black hole. So I don't know what's going on, but it's just a fun fact. So I think there's a lot of things to be understood from this formula. Okay, so that's all I have. Thank you.
Questions?
Sure. Yeah. Well, it's still two dominant saddles if a very young, a very early time or very late time. No, that picture is still correct, right? I'm just saying when you're near the transition, when all the other saddles are relevant, maybe there isn't a single semi-classical geometry, therefore, or a single QES surface that you can make sense of to say the entropy is computed by the generalized entropy of some surface, because now you have a superposition of all geometries in between them. You can't say a single one is the relevant one. So what this formula says is precisely that, right? So it sort of says you can do sum over all of them, or let's say the formula says if a particular one dominates, then where's my formula? Let's see. Yeah. So here, for example, if a particular one dominates, you just have a product of the matter sector times the gravitational sector, and when you take the log, it becomes sort of like a generalized entropy, one plus the other, right? But now, when every term is important, yeah, you need to sum of them up, and yeah, and the solution is something else. Yes.
This is probably a really ignorant question, but I'm just trying to get oriented relative to what Chris has suggested in their paper. They also, I think, gave sort of an argument from the point of view of probabilistic ranking, why there would be large corrections sometimes. Is this just much more general, or?
Yeah, I think so. So what they did is that they argue when the QS formula is correct, but they didn't give a prescription for what to do when it breaks down. Okay.
So there was no gravitational mathematical calculation of the entropy. It was just an exhibition of the fact that the replica breaks down.
I think I heard you. Yeah, we gave arguments for we gave some arguments of what happens, like when it's correct, when it's not correct. And then this seems like a really nice path interval argument for those regimes that we didn't get. I feel like this is a more powerful.
But it's a path interval argument either way, right? Is the difference that you actually be in the regime where the usual formula doesn't work, or do you guys?
Oh no, yeah, we don't have a general prescription. Yeah, we have.
Yeah.
I see. That's it. Yeah, I agree with that. Right.
Okay. Thank you.
Okay. Yeah.
Have you identified other observables that might be sensitive to the full resummation of all the replica symmetry breaking contributions?
No, but I think, for example, what Vijay talked about, or negativity, or various other things that people use resolving trick to compute, might have a chance to be upgraded to this version. So yeah, maybe one should try to see if there's one can do the same thing.
I'm thinking of something like much simpler, like just compute a 2-point function of operators moved off in Euclidean time. Could they be sensitive to full? I'm pretty sure that they're not sensitive if you consider any single contribution.
Mm-hmm. I see.
I'm imagining here that I'm computing something like, I'm considering a 2-point function, but I'm checking if it like self-averages or not. And if you do something like that, then you. Well, that involves just a square, so it's actually not, it's not gonna, okay, never mind.
I'm not sure. If you write on the mathematical formula, maybe I can tell whether this is applicable. But so you're worried, so you're pretty sure each set will give a negligible contribution, but maybe the sum of them amounts to something significant, right? Is that maybe?
Yeah, let me just make a comment about my comment. The observable I was considering was too stupid. It's just, it's not something that benefits from this replica trick of replicating to n replicas and then the continuation and so on and so forth. So I retract my suggestion.
Yes.
Very nice talk. I have a question about the comment made on your final slide. Which means something to do with permanent, right? Which is to say that the black hole should be a very old black hole describes a random channel.
Yeah. Okay. Sure. So from the replica trick, all I had is the spectrum, right? So I don't really have the operator. So it's like, say, I have the density matrix up to basis. But the spectrum, so in the end of the day, you get something like, for a very old black hole, you get something maybe like this. And the point is you try to figure out what kind of map that, that give you sort of starting from the bulk state, maps you to something else. What kind of map give you a spectrum like that? You just asked that question. So it's more like a holographic map, or I don't know, encoding map, where you put in the bulk state, which give you the wrong entropy, and outputs a state which has the right entropy, and then you try to use the spectrum to sort of figure out a map of this sort. So actually I have a okay. I think it's for a very old black hole. Let's say yeah. Okay. So I think the precise statement is that yeah, it's just you have some. It's just like in the island case, you have the island is encoded in the radiation. So you now just write a encoding map for that, and you make sure this map outputs the exact spectrum I computed using all the saddles, and it sort of fixes this map, and this map is like a random channel that. Yeah. Okay, yeah, this is something else. Okay.
Other questions? If not, we can thank Jinzhao again.